recouple concept and strategies. Without further ado, I'd like to begin the lectures. I'll turn over the introduction of our principal speaker to my colleague, Giovanni, and it's my wish that you all have a great and productive conference.
Right, just a couple of words about Mike. He, of course, it needs no introduction, but it's me. I mean, I was very fortunate to be one of his PhD students at Duke some 20 years ago, maybe more. And I've been one of his greatest admirers ever since. And I admire his way of mentoring students, challenging them with difficult research problems, but at the same time supporting them and generously sharing with them hints and help and his research ideas and insights. So his mentoring approach has produced many outstanding researchers, many of whom are with us for this conference, actually. And I also a big admirer of Mike West, the researcher. And under the broad umbrella of Bayesian inference, he has published an incredible number of groundbreaking papers in areas from Bayesian nonparametrics to statistical computing to high-dimensional inference and many more. However, his long-term research interest, the main interest is in dynamic models for time series analysis. And his book with Jeff Harrison, the Bayesian forecasting and dynamic models, was published first in 1989, and it has been cited thousands of times, and that its second edition in 1997, and it's still the to-go book for researchers and practitioners in the area of Bayesian time series analysis. He later published another book with Raquel Prado about the same topic, and he has the vast majority of his papers are in Bayesian analysis for time series. And what is fascinating is in his research paper is the perfect blend of theory, methodology, and applications in such diverse fields as econometrics, finance, climatology, neurosciences, genomics, and many more, you name it. He has applications in all different kinds of fields. And his papers are always driven by real applications, and the theory and methods are developed with the purpose of answering specific relevant subject matter questions. And the theoretical developments in the papers, while deep and highly original, are only as general as needed to answer the given questions, not more. And the clever, complicated models proposed in his papers are sophisticated enough to allow to extract the relevant information from the data, but not more. And the simplifying assumptions and computation approximations that sometimes are introduced in his papers are exactly those needed to find an answer to the question without blurring it in oversimplifications. So simplify enough to find a solution, not more. So this perfect interplay between deep theoretical results, highly complex models, and substantive applications, which is his trademark in his research papers, has always struck me as a form of art, this perfect blend. And we are very fortunate to have Mike West here with us for the next few days to share his insights about recent developments in the area of Bayesian dynamic models. Welcome, Mike.
Well, thanks very much. We're on time, which is good news for all of us. I'm really delighted to be here. I was delighted to be invited. It's actually my first visit to the University of Arkansas, and the research in statistics activities here indicate a positive trajectory for the coming years in education and in research. The area is booming. and I understand a little bit. There's some high-tech flavor to that, but it's probably not so well known outside the area, so keep it quiet and do it. When I decided to, on the topic, of course, I decided on time series and forecasting. I told Giovanni that I'd talk mainly about applications in sort of economic and businessy areas. And I understand there are some representatives of local business community here, and I'd be happy to chat about some of the more recent developments offline with anybody after the meeting. So Giovanni asked me to, so Giovanni was working hard yesterday. Some of you may not know that he gave a 4-hour tutorial to...
Actually, it was split with JD and I.
Okay. All right, a tutorial on a number of things, but presumably including dynamic modeling and forecasting. And he asked me to make sure that the first lecture was high level for those of you who are students and don't know anything about the topic. So that's what we're doing this morning. And then a little bit in the afternoon, we'll segue a little bit into the main theme of the lectures, which is scale-up of Bayesian forecasting models, with an example, just to nucleate the ideas and exemplify them. There is recent research who starts later today and tomorrow through Saturday. And Giovanni said something at the end that isn't quite the way I saw what I was supposed to be doing. He said, I'm going to give lectures about recent research in the field, rather than give lectures about some of the research that I know well, which is predominantly research with collaborators and students of mine. So some of you who flew in from the West Coast can sleep for the next 75 minutes because that's a bit faint. Is it readable back there, Carol? By the way, do I need a microphone? No. Good. For those of you that this is really the sort of stage setting and looking back about 35 years, then I'll be talking a little bit about developments some of the audience members have been involved in over the last 15 to 20 years, and then we'll come up to date at the end of the session this morning. So I'm interested in time series, forecasting, analysis, and other goals that we'll make clear as we go along. And the sort of 3 last talks really hit on the scale-up issues of wanting to build customized, focused, goal-focused models for increasingly large dimensions for forecasting time series, so for monitoring dynamic data, for example, on networks, and complicated structured time series. The term hierarchical has various interpretations in statistics, but linked series at different levels of aggregation, for example. And some of the areas that some of the areas that, the examples that will be infusing the talks come from financial, some of them are commercial, and if there are people interested in dynamic models for time series data, event data in biology or neuroscience or other areas, of course the model domain is mathematical statistics, and applications come from all kinds of fields. So we'll be looking at, n will always be the number of time series in a vector, and we'll be looking at some history today, this morning, just some basic ideas. I've really got 3 themes and concepts to hit on. And then I'll be talking about the limitations of the standard ways that we've been doing things for several decades when it comes to scale up. In case you don't know much about the field, I pulled out and slightly updated a couple of slides here with some company logos, which represent groups that have been involved in using Bayesian forecasting methodology, state-space models, decision analysis overlaying that, in finance, both in big banks and hedge funds, in economics, and other communities in that general area of eco-finance. I believe we have some people from local companies here or coming in later today. And some of those companies, at least one of them is represented here, and I'd be happy to talk about the things that I know have been happening in one of their research groups over the last few years with very, very relevant kinds of problems for the models and ideas of Bayesian forecasting. So we'll have some notation All of my vectors are column vectors, usually lowercase Roman symbols, and my matrices are uppercase bold, or they can be Roman or Greek, depending on context. So the sort of central class of multivariate time series models are conditionally Gaussian, conditionally linear state space models. So the f function in this slide will become a linear function. Linear in the theta matrix there, which is a set of unknown time-varying parameters or state variables that characterize the model. And the x stands for things that are known. There'll be conditionally Gaussian models in which there's always a plus epsilon, and that's a zero mean Gaussian, with a variance matrix whose inverse is going to be called omega. And everything is subscripted with t. Everything is time variable, potentially. In Bayesian statistics, we call omega the precision matrix. And it's a natural object to be concerned with modeling, and we'll see that in force this morning. So it's a vector time series. The theta contains, it could be a vector or a matrix, contains time varying and constant parameters, so we'll generally call that the state. The x's are known quantities, and the omega t is a precision matrix. So fix that notation, that'll be on several slides. Be using the same notation throughout the throughout the lectures that use these models. First order Markov models in a state space framework say that everything you don't know that's potentially time varying evolves in time according to a first order Markov evolution. A conditional distribution, everything's density functions in my simple calculus, in which tomorrow's states, and now its states, and what I will call the volatility matrix that this precision matrix is, evolve in time based on where they were yesterday, conditionally independent of the past. Bayesian analysis of state space models focuses heavily on the sequential analysis, learning from data through time, understanding structure, understanding model fit and misfit, and then forecasting. And we usually use the term prediction. It's a little bit sexier than forecast in some communities. So at any time t with past data available, we're interested in forecasting ahead. Macroeconomics, we're interested in forecasting each of the next 36 months of a set of macroeconomic time series. Conjointly, we want to know the path of the economy into the future. And that's going to be conditioned on all the information we have at the time. So models are structured with interpretable states. The parameters are meaningful, regression coefficients and other quantities, trend components, seasonal components. And the model breaks down variation in the data and variation over time into that is described by the way in which the states change, the parameters change, and that which is residual or unpredictable. And for all of us today, that'll be conditionally Gaussian. The sequential specification of models is important because as you learn from data, you might want to change your model, incorporate new variables, throw some other ones away, change the structure. So models should always be thought about like that. They're evolving quantities, they're not simply mathematical formulae that are supposedly fixed for all time. This picture just really encapsulates the essential sort of sequential structure. It also tells you that we're really working in state space models or hidden Markov models. I've dropped the omega t matrix, the volatility matrix, the precision matrix from this cartoon just for clarity. The state is evolving in time according to a first order Markov model that has been specified, but may have some parameters that need to be understood from the data. And then conditional on the states at each time, the observations that you see on the time series are conditionally independent. So that's a canonical picture for a hidden Markov, first order Markov model. I described the sequential nature of it, and for today, I'm simply going to refer to known theory of manipulation of these models when the f function is a conditional linear function in the state theta t. And of course, the model then becomes a linear Gaussian state space system. If you have an engineering background, it's a linear system where Kalman filtering ideas apply. And that's just part of the mathematical machinery of the bigger picture of Bayesian learning and use of these models. In a multivariate system, the thetas will be matrices or vectors that evolve according to conditionally linear Markov evolutions, and the omega matrix that is defines the covariance structures through its inverse across the series will have some known distribution theory associated with it, and there are classes of standard models that are used for this based on Wishart and inverse Wishart theory. So learning. If you were at Giovanni's tutorial yesterday, you'd have seen some of the essentials of this, probably in mathematics rather than in pictures. So this is the guts of sequential analysis and learning from a Bayesian point of view in a conditionally, in a hidden Markov model generally. Again, I've dropped the omega t matrix just for the clarity on the slide here. So here we are at day t. And the D here is the information I have. It includes all of the past data, but it includes other things that I might have used and learned from and included in the modeling enterprise. So it's my information. So at day t minus 1, I have an information set, and it's summarized, the relevance of it for the modeling and the forecasting is summarized in terms of a posterior distribution for the state at the time. Okay. I'm talking about yesterday. This is today t. So the model gives me this little directed graph where the state evolves from yesterday to today, and then the observation is generated conditional on today's state. And that evolution has a parallel in terms of the distribution theory, that yesterday's posterior for yesterday's state becomes today's prior for today's state, based on the historical information. Coupling that with the model for the data then allows me to just use probability calculus to predict into the future, to do exact calculations in some models, direct simulation most of the time. Then I move ahead, I see the data today. I learned about the closing prices of the stocks in my portfolio on the S&P, and I update my information set accordingly to incorporate that new data. That therefore updates what was my prior for today's state to my posterior for today's state. And you see all I've done there is change the time index from the start of the slide to the end of the slide to complete the one-step, one-day evolve, forecast, and then update cycle of the hidden Markov model. And then time progresses and I move on into the future. Oh, I see you're taking a photograph of the slide. I think the slides are going to be made available to the audience if they want. Yeah. Yeah. Okay. Unless you want to photograph me, you get one for free. Okay. So a couple of examples. Workhorse example is what's called a time-varying vector autoregressive model. Purely empirical statistical model, no explanation of where the data is coming from or going, simply predicting the future based on the past, nothing more. Well, there's something hidden in there because the way you structure the parameters, the states here, can go deeper. But I give you a conditional linear, conditional Gaussian model where perhaps the values today and yesterday of your stock prices are short-term predictors of tomorrow. Okay? 1-2 day momentum prices. And they're potentially covariant. Okay? So that gives you lagged predicted behavior. Think about it as arrows coming from the past to the future. Networks of relationships, purely empirical. And then the residual has this precision matrix, which we're now going to talk about as a volatility matrix because it's changing in time. That talks about the contemporaneous relationships. Okay? That talks about dependencies within day t. I use the term workhorse. This is the most important model in empirical macroeconomics and monetary policy and other areas of macroeconomics. Since the 1980s, since Ben Bernanke and others wrote a few papers on it in that context. Chris Sims, Nobel laureate, he's a statistician, but they don't have the Nobel Prize for statisticians. Basically defined this as a major way of thinking about approximating macroeconomic theory. And you can change the model by adding components. You can make it more complicated with external variables. You can make it nonlinear. You can make it mixtures of such models. You can elaborate it in many, many ways. But it still remains as an empirical tool for both exploratory time series analysis to understand structure in data over time, how it changes, how the states change. Here, the theta matrix is comprised of these lag coefficient matrices. So it's a canonical model, and we'll be referring to that throughout the talk, and then both this afternoon and tomorrow we'll be using variants of this model. One area I mentioned, most of the examples come from other areas than biology. This is from neuroscience. This data is EEG data from neuroscience, and I think we might hear something about that kind of data later in the conference. It's a major tool in this area for looking at time-varying relationships of, in this case, EEG signals spatially related around the brain, how their relationships evolve in time in terms of both lagged relationships across series and contemporaneous relationships. That's really the only slide I have that comes from that kind of area. Here's the second class of models, which is in fact richer than the time-varying vector autoregressive models. It's called the exchangeable time series models. It's been around for 40 or 50 years. And a lot of macroeconomic history to it, as well as a lot of business forecasting history. And it's still widely used as a subset of the more general models. This theta matrix, now we've gone back to the general notation, contains the vector autoregressive coefficient matrix as a special case. It's just another way of writing it. Okay? So F here is things we know. It could include lots of lagged Y's. Suppose Y is a vector of 14 currencies, exchange rates relative to the US dollar on day T. We'll be using that kind of example throughout. And we might regress that on yesterday's prices and the day's prices. There's 1 to 2 to 3 day momentum typically in daily foreign exchange series. But we'll have other things in there as well. We'll have relative interest rates between the country and the US. And we'll have political indicators and things like that. Okay? So this is a class of models that includes time-varying vectorial regressions, but goes beyond it in a number of directions. Here, theta is explicitly a matrix. Y is a column vector. F is a column vector. And the volatility matrix is what it always is. But what you can see here with that example, if Y is sort of 15-dimensional, and we've got yesterday's prices and the day before prices in there, that's 30 dimensions. I mean, each country's got its own indicator, that's another few. That F vector is getting big, so the theta matrix is getting big. So vectorial regressions and this more general class of exchangeable time series models, like a lot of empirical statistical models, are challenged with dimension. As the dimension of Y gets bigger, you've got to think carefully about constraints on parameters. And here, for goodness sake, the parameters are time varying. Okay? So the way you structure priors and constraints and pieces of the model become critical if you want to scale. And then segueing into, or raising for the first time, one of the themes for later on, well, a lot of those parameters are irrelevant in that theta matrix. So let's get rid of some of them. Let's figure out how to do that. Okay? Let's think about sparsity with a goal of breeding parsimony into the model. If the data thinks parameters are really not relevant, then figure out how to get rid of them. Okay, so one of 2 or 3 touch points on some of the research in the last, say, 20 years that has addressed this sort of scalability problem from the point of view of putting zeros into matrices, from the point of view of what we these days call sparsity modeling. In the same model context, I've got a little example here. It's an old example of currency exchange rates. Let's suppose it means something else today. That doesn't really matter what it is. These are European and Asian countries. That picture is a graph. It's an undirected graph. And it isn't a complete graph. There are edges missing. And in statistics, for those of you that are not so involved in statistics, but are more coming from the mathematical sciences. Some of the most, in my opinion, the prettiest mathematics that statistics has been part of developing in the last 25, 30 years has been in graphical modeling generally. And that began to have an impact about 15 years ago, maybe a little more, in time series, in multivariate time series, addressing this question of, can we get rid of parameters? Can we put zeros into parameter matrices? So if you have a Gaussian distribution with a precision matrix, the inverse covariance matrix, with some off-diagonal zeros, they relate to conditional independence. So this picture represents that. The edges are there where the precision matrix has a non-zero element. So we've got 11 series, it's an 11 by 11 matrix. We've got a blue-white image where blue is an edge and white is a missing edge. The adjacency matrix of that undirected graph. So the one-one correspondence then is zeros in omega t off diagonal in column I, column and row j, correspond to node I and node j having no edge. And in this picture, this would say that the exchange rates relative to the US dollar, the exchange rate of the New Zealand dollar, day by day, conditional on that of the Australian dollar, is conditionally independent of everything else. So if you want to predict the exchange rate of the New Zealand dollar, along with other things, then get hold of the exchange rate of the Australian dollar. It will be useful. And when you have it, you don't need anything else. That's the conditional independence. So you can see if you've got a bigger time series, say 400 by 400, this omega matrix has lots of zeros, you've got lots of conditional independence. So sparsity corresponds to conditional independence, and that's not just a reduction of dimension if the data likes it. Okay, it's an improvement in interpretation and helps you think about what the model actually means through conditional independence. Some of the people in the audience know a lot about this and a lot more than me about it because they're involved in some of this research over the years. And this is still, I've just finished teaching in the last 2 weeks, this is an introductory modeling course. The last 2 weeks was on graphical models. Very, very central to scalability generally in statistics. But you can see that if you get into these models, and I'll give you just some pictures of showing you why they might be interesting beyond just the interpretation point of view. You see that that graph becomes a parameter. I could have drawn a different graph. I could have taken a few edges away and added some different ones. It's a graph on 11 nodes. So who knows what 2 to the 11 choose 2 is? It's 3.6 something, I'm sorry, it's 3.4 something times 10 to the 16. Okay, so it's a big number. So if you're going to use this kind of graphical modeling idea, you've got to think about where the graph comes from, or where a collection of graphs come from. The graph becomes a parameter. And this idea of building parsimonious models with sparsity kicks you because all of a sudden you've got this huge dimensional problem lurking underneath that you've got to somehow address. Should you address it? Yes. These are pictures and summary from several papers over the years where in short-term forecasting of financial time series, with a focus, a very specific focus, we don't just care about forecasting, feeding into decisions of portfolio revisions to invest your fortune, sparsity can help. This is cumulative returns over time, where the top one, of course, is a sparse graphical structure underlying a standard model. The histogram in the middle, the red is risk on models that have all of their edges in the graph, while the blue is the risk on a model with lots of zeros in the precision matrix, a sparser graph. So models that utilize sparse structure of this kind and others improve portfolio returns and reduce risk. And the third graph is related to turnover of the portfolios, and it has costs when there's a lot of turnover. So the sparsity kicks in there too. It constrains the decisions in smoother ways. So you should be interested in them. And this gets to the second point that I want to emphasize in some of the talks this week. Those pictures were about portfolio returns. There was no picture there that had statistical measures of how good a model using the graph was compared against a model that doesn't use the graph. They were in terms of dollars and risk associated with the decisions that the models were being used for. So I'll return to this theme a few times because it's really relevant for statistical modeling, not just for scalability, but comparison of models generally. And as you're scaling data, you're necessarily scaling the dimension of the model space. It gets harder and harder to think about how to choose models. So statistics is not just about modeling. I use the term belief analysis here for modeling, inference, prediction, using the mathematics of probability theory in those enterprises. Michael Goldstein, who's retired recently at the University of Durham in England, coined the phrase belief analysis, and I kind of like it. That's the way I think about models when I'm building them for applications. You know, they're my models. They're not something that is mathematics and I'm plugging data into. Well, what's the yang of statistics? It's decision analysis. It's why you're modeling. Giovanni hit on this central theme a couple of times in his introduction. Okay, we build models for a purpose. Sometimes it's exploratory data analysis. That's fine. And many different statistical metrics to score different models are relevant as a way of exploring and understanding data. But in application, if you're forecasting internet sales for all of Walmart, or thinking about how to pull together information to improve macroeconomic forecasting for all of the US, then it's decisions and endpoint users and uses of the models that should arbitrate how you compare and contrast models, at least to a degree. So decision analysis coupled with belief analysis. And sometimes that leads you in different ways than if you take a purely statistical view. So most statistics teaching, we teach students to, well, here's 15 variables in a regression. Let's look at all possible subsets and compare them with different statistical metrics. Okay. If you then add in decision metrics relevant to the use of the model, you may find different models of interest. Okay, so here's an old example. I should update this. I've got lots of extensions of it, but it goes back a few years. And this again has to do with portfolios. The same kind of model. I'm not being explicit about this now, but now we're in 30 dimensions. This is monthly data on a particular set of mutual funds over the years. And here we've got quite a few more models than 3.4 times 10 to the 16. So the model space, the number of possible graphs, the number of possible sets of conditional independence assumptions in omega is rather large. So you can't look at all of the models. And you shouldn't want to on a purely statistical basis anyway. And this picture hits on this point. So here are 200 models, 200 sets of conditional independence assumptions. So it's a 30 by 30 adjacency matrix in this graph. Where are the edges in between these 30 mutual funds? The vertical axis is the standard Bayesian metric that feeds into lots of other measures of statistical model fit. Okay, on a log scale, it's the marginal likelihood of the data given a particular model. And here, each point is a particular dynamic linear model, multivariate 30-dimensional model, but they're distinguished by the sets of conditional independence assumptions. So each one is a graph. So there are some high probability graphs, and these are the 200 highest probability graphs that were found in a particular analysis. There are a lot of them, as I said, so we didn't find them all. Along here, this axis says, well, there's 30 nodes in this graph. How many edges are in this graph? So this is the percent of edges. Okay. 30 choose 2 pairs. And all of these models are around about 25 to 30%. So about 2/3 of the edges are missing. Okay, so there's a lot of conditional independence in these high probability graphs. The blue spot at the back is the graph that was embedded in the calculation as a baseline, which has all of the edges. So this is the standard analysis that has been done with these models for decades. Okay? No conditional independence no sparsity. Okay? And you can see it has low probability relative to most of these graphs. And of course, it's not sparse. The third axis is from a particular portfolio decision analysis that looked at risk and return over a period of time with these data. And so the lower risk graphs tend to have higher probability. So statistics corresponds to low risk. That's a good thing. If you care about risk as part of your portfolio decision, which most of us do. But then the color coding tells you that a lot of the higher probability graphs generate lower return. A low risk, low return. And you probably want red graphs, which are not necessarily the highest probability. So the decision-guided comparison of models may lead you into a different part of model space. And so to nail that particular point, let's look at this picture. So this is my 30 by 30 adjacency matrix of a graph. White is 0, black is 1. The shading is on a probability scale. So looking at lots of graphs and calculating their probabilities as illustrated in the earlier picture, this gives you the probability of inclusion of an edge in the graph. And I've ordered things so it's pretty, and you can see it's fairly sparse, 30%, 25%. But where the edges are indicated, they're fairly short. Most of it's sort of black rather than orange. And where it's white, it's fairly sure as well. So if you're a statistician and you're doing an exploratory analysis and you don't want to use models, you would stop there. Let's do a similar calculation, but now guided by the portfolio outcomes, the returns of the portfolio. And this simply takes, I think it was 1,000 graphs that make the most money. And just look at the frequency of occurrence of edges across those graphs. And the ordering is slightly different just to make it pretty. And you see two things. Well, you see three things. You'll see it's different, even modulo the ordering. You get the impression that it's sparser. Right? Pretty clearly sparser. And the way I've ordered it, you'll see that this particular series, on its row, most of the column entries are black. Not all, but almost. So if you think about that, what that means is that particular series, and I'll give you its name, it's US growth, it's an index fund, it's cheap to invest in, okay, it's not managed by highly paid managers, and it's, many of the other series are conditionally dependent on it in the 30-dimensional distribution. So for predicting the returns on a monthly basis of most of these funds, it would be very useful to know what the return is on this particular fund. And if you know it, you might want to know one or two others for any individual fund, but it's a hub. And if you think about the graph, it's got lots of edges, so it has plays a role of a hub in the graph space. So if anybody cares about this kind of data, the red funds, the red series are managed funds, and the blue series, I'm sorry, it's US growth. It is managed, but it's a cheap managed fund. Basically, it's a metric of GDP. So if you're interested in this, and you're interested in thinking about, well, how do I improve my forecasts with respect to a portfolio decision of a collection of equities, okay? It's nice to start thinking about, well, what would I most like to know about outcomes next month? Okay, in this case it would be US growth fund, and do my best to predict that, and use that to then predict the others. So the third point then here is back to parsimony from the point of the decision analysis as compared to the statistical metric of weighting model, of comparing models. We're led into a region of higher parsimony, more sparsity. Okay, Okay, so from the point of view of modeling a time-varying covariance matrix on its inverse scale, precision matrix, get rid of more of those parameters, because when you come to feeding that into the decision analysis calculations, they're just injecting noise. Okay? Data says they might be interesting on the statistical side. The decision analysis benefits from moving them out of the conversation altogether. So it's a slightly different take on thinking about sparsity in empirical modeling, I think, than is typical in statistics. So if you remember one thing from my talks this week, remember this slide. Okay? Model comparison, R squared, analysis CP statistic, Bayesian model averaging, all kinds of cross-validation. That's in the realm of statistics, not in the realm of use of statistical models in application. Okay. Let's come up to date a little bit then. So I've been embedded in the middle part of the first decade of the millennium. More recently, I think we'll see some talks at this conference. The whole idea of building sparsity into models by using probabilistic generative models to allow the appearance of zeros in parameters, it's everything, right? If you look at the top 15 statistics journals in the last 15 years, they're full of it, okay? We have some experts locally, I know, who think about taking parameters and building models that say some of them can be zero with some probability, non-parametric Bayesian models, all kinds of things. Okay? So the idea of sparsity modeling is entrenched, and it's a central sort of theme in statistics, in application as well as research. Okay. So more generally thinking about sparsity, what I was talking about in terms of some of the history of exchangeable time series models with graphical structures. That graphical structure is on the inverse of the covariance matrix. So let's think about the same idea now applied to the state matrix, the regression parameters on lagged values and independent variables, seasonal factors, and all kinds of other things that might be in theta t, many of which might be, at least after some transformation, irrelevant from a practical point of view, from the point of view of forecasting or decisions based on those forecasts. So irrelevant means that while the data might like them a little bit, they're practically insignificant. Okay? A modeling analysis may say, well, like the graphical model, well, these edges are, probably 35%, 40% probability. But the acid test is then how they impact when you use the models in forecasting decisions. And usually, doing more to constrain, building more sparsity than statistics would guide you to is a good idea. So I mentioned Bayesian variable selection models and methodology associated with that. And there's also, of course, the whole optimization view in statistics, that we can put parameters to zero using methods, lasso to the power 15, whatever the latest and greatest are, which are methods of plugging in zeros. And that's of course, a central area as well, although that admits from the start that we are going to then ignore uncertainties in some dimension of the analysis that can play a really important role in use of models. Okay. So there's been a large array of developments in time series in the last decade or so in this line. I'm going to allude to one or two of them in a multivariate setting. And I'm starting now to think about, well, hey, I've got this 30-dimensional vector, and I've got all of these predictors, and I've set it up in a standard time-varying vector autoregressive or exchangeable time series framework. And I haven't put a lot of thought into what actually goes in there. And maybe it's time to step back and think more carefully about each individual series. Customize the model a little bit, especially now as we're beginning to think about more sparse structures. Some series may demand more sparse structures than others. I mentioned latent factor models, and that's coming as one of the examples in a second. So this is a bit of a bully of a slide from the point of view of mathematical notation. It's the busiest this morning. I'm just laying out here a class of a set of classes of conditionally linear, conditionally Gaussian models that go beyond the models we've been just sort of alluding to today. So everything remains conditionally linear and conditionally Gaussian. We might have some trend component. So each of the series might have some time-varying trend. Maybe there's some other, depending on the context, there might be some seasonal components and some other things that you want to put in there. And then a state parameter matrix A that represents elasticities, regression coefficients on a set of predictive variables. Our old friend, a time-varying vector autoregression. I've changed the notation slightly because this theta matrix now is going to be all of these things put together. With some like D there, 30 series or 300 series, you might want a few lags. Dynamic latent factors are very central in a lot of research in economics and finance, a lot of applications, a lot of applied models. Bernanke hasn't won a Nobel Prize, but if he did, it would partly be for this kind of thinking. So here, ET is a piece of the state matrix, and the phi for factor, represents some underlying Markov process, or some underlying hidden process that may not be Markov, whose evolution has to be understood from the data modulo the specification of a prior, but whose impact is shared across the series Y. For example, the standard model, let me put the words up there, it's a bit of an ugly phrase. This is called FAVA modeling, or factor augmented time-varying vector autoregressive models. Models that have this component and this component. And I'll give you an example of why that might be interesting. For some of you, it might be, oh, well, that's going to be a big, overspecified, unidentified model. I'll give you an example that might interest you. So I've got a plus or minus. Any particular model might have one or more of these components, but there's a rich class of very flexible empirical models that build on time-varying vector autoregressions, add latent factor processes. And there's a lot of use of these models in spatial time series, way outside economics and finance. So then, of course, as these things as Y gets bigger, these matrices get bigger, and we've got to start thinking about constraints. So how do we do that? How do you put zeros in the AT and the BJT and ET as well as omega T? Big, hard model on set dipolars. So the example comes from one of the series of papers with some neuroscience data as well as finance. This is a collection of currency exchange rates. We've got the oil and gold prices measured in specific ways here as well, some oil currencies. And we're again interested in short-term forecasting portfolios. So I'll start with a model that I wouldn't use, and then segue into the model that gets us into this idea of decouple, recouple. So in a particular paper, a series of papers, this class of models was exploited, where there's a local level for each of the log prices. Then there's a predictive component that says if I know the price of gold and oil yesterday, I'll use that to predict the short-term fluctuation in the currency prices, as well as themselves. And then there's a latent factor component that is, in this example, a 3-vector. So it's a 3-dimensional vector autoregression with time-varying parameters, just a lag one. And you'll see this isn't omega T anymore, this is a lambda T. Lambda is a diagonal matrix of precisions, one series at a time, that may be time-varying. So that would be a very standard model in a lot of macroeconomics and other areas. Here's a different model. Okay, this term is different. Okay. So this is a 11-dimensional time series. Okay, whatever it was, 11. Suppose it's 11-dimensional. And that is the 11 by 11 identity minus a square matrix gamma, which looks like this. It's a strictly upper triangular matrix where some of the upper triangular elements can be 0. And the black indicates non-zero. And where they're non-zero, there's a T on gamma, but potentially time-varying numbers. And where it's white, there are non-zeros. So it's a slight modification of the previous model. And what this does is it specifies what in economics and macroeconomics is called the structural form of a fairly elaborate multivariate dynamic model. Okay? Where on the right-hand side in these terms, we've got the usual ways of thinking. But on the left-hand side, you'll see row by row, if we take the first row, we've got y1t here. Well, when we hit it with the first row of I minus gamma, that's going to give us y1t minus a linear combination of the other y's on the same day t, but only including those where there's a black spot, with whatever the number is hiding beneath that black spot. Okay? So that's building a relationship between the y's contemporaneously. Okay? And on the next slide, we'll see how this recouples. It begins to get us into the decoupling because we're saying row by row, we are going to choose that black-white pattern in each row to relate to the contemporaneous dependencies amongst these series. And as we go down, we're thinking in a sort of customized way about each individual univariate series. This has some benefits in computation, and I'll allude to that, but it's more important to think about the way of thinking. It's not new. There's nothing, by the way, for PhD students. How many PhD students got up early this morning? All right, so somebody may have told you this. If they hadn't, let me tell you it. When you write something in your thesis or draft paper or even in some notes to talk about with your advisor, and you think it's new, give it a name. Okay? For example, decouple, recouple. It doesn't matter if it's not new, as long as you think it's new. Okay? So we're not talking about anything new today so much as we will be later on this week in terms of the decouple, recouple idea. This is a structural modeling strategy, which has been around in macroeconomics for decades. Okay, let's go to the reduced form of the model, which is what I will now call the recouple step, and move that I minus gamma over to the right-hand side of the equation. Okay, to get the implied predictive part of the model, I'll focus on in this slide what happens here. This is a diagonal matrix. The precision matrix becomes this Cholesky-style product. Okay, and this is the reduced form of this set of equations from the previous slide. So for about 15 or 20 years, well, back since about 2004 or 5, that's right, about 15 years, building models of covariance matrices by treating the Cholesky parameters as primary has become more and more popular. This is sort of doing it the other way around. This is directly specifying a set of relationships and just noticing it's a Cholesky-style construction. But importantly, this will be sparse typically. This omega t will be sparse when gamma is very sparse. Okay? So you see we're sort of also segueing back into the graphical model kind of structure. The final point I want to make, this is not going to be a big theme in several of the talks, but it will be there this afternoon and tomorrow, is that this choice of where zeros and non-zeros are in parameter matrices can be different at different points in time. And I'm just bringing this in primarily because this was really a point of nucleation of this whole way of thinking of decouple, recouple a few years ago, where the idea was to extend these sort of modeling ideas to allow the sparsity pattern to change. Okay? A relationship between a predictive variable and a response variable may come and go. All you have to do is look at economic and financial data before the Great Recession and through the Great Recession and after to realize that. Just look at the Japanese macroeconomy for many years. So there are many approaches, and you may see some of that. I think we're going to see some of that today, actually, for what we can now refer to as dynamic sparsity model. Sparsity itself is a dynamic parameter. And there's been a lot of groups over the last few years that have been pushing Bayesian thinking in different ways in that area. A lot of very nice work. One of those themes was based on so-called latent threshold modeling. And for those of you that don't know about it, the idea is simply that there may be, say, a regression parameter, an elasticity in your model for one series, okay? That is basically irrelevant over a period of time. The gray shading means it's outside the model, okay? So you don't really care what it looks like as a process over time. It's a latent random process that you can try and estimate from the data modulo model and priors. But if it's outside the model, you've basically selected a zero in that black-white image. There may be another elasticity on a different parameter that is varying over time, and it's surely in the model all of the time. So there's a white spot in the matrix corresponding to that parameter. And then there may be others for which, well, it comes and goes, so you're not sure. It's 50% or 70% in the model. So statistically, it's playing a role. But it's down there in, towards the level of noise, and it may be something to look at removing for particular decisions. So back to the example of this latent factor model for these FX, oil, and gold, just to finalize the example. This is the oil price over those years. This is the gold price. They are predictors of these several currencies. And they're useful for some of them. And they're useful in time-varying ways for others. I said the phi vector was going to be a three-dimensional factor process, a t time-varying AR1. Let's just look at this trajectory. This is an estimate, the posterior mean over time, of factor 1. The first element of phi t. And if you look at that, you say, it looks pretty similar to the oil price. It is similar to the oil price. They're very highly collinear. But the model, mixed with the data, says the oil price is useful as a short-term predictor in these currencies, some of these currencies. But it's getting at something imperfectly. And the model said, this data tells me I want to put in a latent factor that sort of adds to that pattern and improves it slightly for predicting some of these currency fluctuations. And if you look at factor 2, you'll see it has, it's not the same, but a similar form. Factor 1 and factor 2 are dependent. They're related. Those of you that may know something about latent factor modeling will know that often people use independent factors because of mathematical reasons. Sparsity in structured models in the component states that relate factors to observations allows a more general view of factor modeling where factors can be dependent. And data and decisions data in a decision context can lead you to benefit from that dependence. Portfolios are improved in that example. I think that point has been made. I wouldn't be showing you that example if they weren't. Okay. So, the last couple of minutes, let me say why we're going to be talking about what we're going to be talking about in my talks for the next couple of days. Hidden behind all of these examples, and there are no references in the slides, of course, you can get references. Lots of computations. And I had a 95% rule, that 95% of the R&D in these kinds of models that I've just exemplified. Already alluded to model search over big sparse model space and Bayesian sparsity modeling and non-Bayesian sparsity modeling. 95% of the time is developing computational implementations and trying to figure out why it's not working. Okay? Many of you know Markov chain Monte Carlo. I've got some mechanisms. I apologize for those of you that don't know the acronyms. Markov chain Monte Carlo, big Markov chain Monte Carlo. So in the factor analysis model, every day you take the history of the data and do a big iterative MCMC, and then you do it again, and you tune it, and then you do it again, and eventually you're happy with it. And you use it to produce forecasts and feed into the portfolio decisions. Then you move ahead one day and do it again. Okay, I mean, GPUs and CPUs, cycles are cheap, but the R&D needed to get to that point is not. Okay. A lot of it's standard, and in the Bayesian community we're very familiar with these methods and this way of operating. And there are all kinds of lovely, lovely tricks, forward, backward algorithms that are used in these methods, and all kinds of things. And critically for us this week, this idea of beginning to think about each series one at a time, conditional and contemporaneous values, as a way of breaking down into sets of univariate series, the beginnings of decouple, recouple thinking, is a real enabler from the point of view of allowing you to implement these big computations. But it's a big, big R&D enterprise. Oh, I already said that. There are other things you could use. There are smart tricks like importance sampling that sometimes can be useful, but now we're getting into the weeds of applied research. I'm assuming that, I know some of you have some interest in sequential Monte Carlo, which has been a big growth area in dynamic modeling for 30 years and lots of other areas now. And it's a very hot topic still, and it has been for all those years. And variance for filtering in nonlinear systems over time, based on very, very smart theory and insight. And a very de rigueur. I don't know, some of you will know what ABC means. It's a whole class of computational techniques in the Bayes, non-Bayes statistics world. It stands for approximate Bayesian computation, if you don't know what the acronym means. Right? Very imaginative name. So that's another set of tools, but again, this is a 99.5 and 0.5% enterprise when it comes to computation, implementation, tuning, sensitivity of the analysis to the computational strategies. And by the way, I don't recommend it. I can say that honestly because I've done a lot of it, published on it, but it's not, well, let's say it's not scalable, and let's leave it at that. So that's part of my perspective, and that's why for a couple of years, and partly it's age, but it's mainly this, that I want to get out of that way of thinking. And as we have moved in, we're 10 years into the big data era, and statistics has pushed very hard to scale what we know works well in small dimensional problems to higher dimensions in all kinds of fancy ways. But in the main, I contend, it's been about pushing computation. It's about investing in that 95 to 99.5% part of the enterprise. I don't want to do that. I want to reverse or revert the balance of time spent on thinking, customizing models, tuning the thinking about what matters and what might not matter, where the sparsity might be or might not, and how things are changing. And one way I started doing that a few years ago was to go back to basics and say, well, look, let's figure out how far we can go with old style modeling where we do Kalman filtering, where we build simple linear models that are analytically tractable. We can do calculations in a whiz and customize models to univariate series as much as we like and invest our time and energy in that. And then figure out how to put them together. Because if we're going to do coherent forecasting and decision analysis based on the multivariate system, we have to be able to put them together coherently according to the laws of probability. So we'll need some thinking about recoupling. So that's it, pretty much. That's the big picture sort of introduction. This afternoon, a little bit of continuation of this big picture, using structural models and going to reduced forms. And the example there is a relatively low-dimensional example, a published example that really helps convey the ideas through a more detailed example. It'll be in finance where there are time-varying effects. There's a lot of model structure uncertainty, where the sparsity is, and so forth. And there are parameters as well we have to figure out, non-time-varying model parameters. And then we'll continue that a little bit in the morning tomorrow with some more recent research-related approaches, which allow scalability and really address a real limitation of the simple structural modeling approach that I've just introduced. That example will be actually 401 dimensional time series. And then tomorrow afternoon, we'll switch gears a little bit. This will no longer be economic and finance forecasting. This will be discrete time series, where the number of time series is the number of pairs of nodes in a network. Okay? So you can scale it as much as you like. And network modeling, generally, probability models and statistical analysis and machine learning methods is of course de rigueur. But this is an area where the decouple-recouple idea morphed a little bit in what I regard as a very important way to enable us to scale basically linearly in the number of network node pairs. The context there is monitoring and anomaly detection rather than forecasting, but it's a nice context for the concept. Then on Saturday morning, it's again a discrete time series, and here the number m of time series is in the hundreds of thousands. Okay. And we spend most of the time thinking about each individual time series. And this is the context of hierarchical structured time series, where there really are relationships across series that come through natural ways of aggregating them across different dimensions. And it comes from commercial sales and demand forecasting. I say, in principle, it's hundreds of thousands. Actually, in principle, it's whatever you want to make it, because I don't know how many things Amazon sells on its website, but every one of those things could be a time series. That's it for this morning. Pretty much on time. So let me just put up a few mugshots of some friends, a couple of whom are here. You can see some things about them there. I don't need to go through the slides, but this has been a bit of a tour of some basics from the very old days, and then the last 20 years or so involving a number of friends and family. And we'll have some more this afternoon, and I'll have some more mugshots. So thanks for your attention, and look forward to the rest of the meeting. Thank you.